Okay, so we're still talking about equilibrium, only this time everything that we will be talking about has to do with acids and bases. So this is, for the most part, a walk down memory lane, which is generally good for you. So first let's get some vocab out of the way. Acid is Latin for sour tasting, and I thought that alkali was Arabic for bitter, but the kids who speak Arabic that I know are like, no it's not. So I don't know what alkali means, but I kind of like that. Maybe it meant Arabic for bitter. Okay, so a proton is the same as a hydrogen ion. A hydrogen ion, if you recall that hydrogen has one proton and one electron. Most hydrogens have no neutrons. So when you get rid of the electron, it becomes nothing but a proton. That's it. So that's why they call it a proton. The hydronium ion is a proton in water. See where they get it? A proton and water becomes the hydronium ion. Now, everything that we'll be talking about is acids and bases are all in solution. So for the most part, you may use these as synonyms. The same thing, yes?
Never mind. So H plus H2O, is that a hydrate or is that
It's a hydronium
ion?
ion.
And is it like a chemical reaction that forms that?
You can think of it that way if you want to. All right, there are 3 acid-base models that we're going to talk about. The first one is Arrhenius's model. You recall Mr. Arrhenius and his equation that I didn't make you do because it was too hard for everybody, and I always got him wrong. He helped you out in middle school and elementary school, and you remember this, an acid is anything that produces a hydrogen ion in water. A base is anything that produces a hydroxide ion in water. That works well in elementary school and middle school because it accounts for the one type of base that you worked with. Well, now you're going to work with some stuff that does not produce OH, or does not look like it has OH in it. So Mr. Bronsted, a man from Sweden who has that cool thing through the O, and Mr. Lowry got together and proposed a different model of what an acid and a base look like. And this is the one that is more pertinent to us in AP Chem. An acid is something that donates a hydrogen ion. It donates a hydrogen ion. A base is a hydrogen ion acceptor. And in order to accept, it has to have a non-bonding pair of electrons. Remember non-bonding pair of electrons? Non-bonding pair of electrons. Okay. So let's say we have an acid and it's in water. You added acid to water like you otter, and this is what happens. The acid, H standing for the proton, and the A stands for any ion, anion, and water are in equilibrium with the hydronium ion and the anion. So I think you remember this from Chem 1. All right, you have an acid and the base, and on the other side you have the conjugate and the opposite. All right, so an acid is anything that donates a proton. A base is anything that accepts a proton. So in order to identify which is which, you need to find out which one has hydrogen. Well, they both do, so there's no help there. Then you need to look at the other side of the equation and see what happens. So HA, when all was said and done, became A minus. The difference is it lost a proton. So it's an acid, and on the other side is what I want you to think of the word conjugate as leftover. And then I want you to think of the other one as the opposite. So the acid will be the conjugate left over opposite base. So if we look at water here, on the opposite side of the arrow, we see that it has gained the proton. Therefore, the water acted as the base, and its opposite, leftover opposite would be the conjugate acid. Okay, remember the conjugates are always products. Conjugates are always products.
So hydronium is acid?
It is right here, yes.
What?
It's the conjugate acid. There are a bunch of different situations, and the question you're asking, I can't tell you always will be anything, because it depends on the situation.
Okay.
Okay? So, you need to know that there are always pairs. Here you have the acid and its conjugate base, the base and its conjugate acid. Make sure you can pair them up. In the following reaction, identify the acid on the left and the conjugate base on the right. Now, B and C are separate and do not follow this equation. A, directions here. Figure this out right now. You have a minute and a half to do so. Okay. When I look at this, HBr and NH3, I need to determine which one's going to be the acid and which one's going to be the base. They both have hydrogen in them, so I can't tell just by looking. But I can tell by looking at what happened on the other side of the arrow. HBr is converted at this side to just Br. It lost or donated a proton, so this makes it the acid, and what's left over is the conjugate, and it's the opposite of the acid, so it's the base. NH3 compared to NH4 plus, it seems to have gained a proton. This makes it the base, and this the conjugate acid. The question asks, what is the conjugate base of H2S? The conjugate base, this makes this an acid, so it needs to lose a hydrogen, one at a time. High school. Negative experience in high school. What is the conjugate acid of HNO3 minus? So this must be a base, and if it's a base, it must accept a proton. Yeah.
Aren't they, another way to think about it is the conjugate acid and bases, because of equilibrium, it means that when it goes the other way, they're now...
I'm going to get there in just a minute. And that's exactly what, where do I want to do that? Soon. Okay.
Are we no longer going to be doing acid-base neutralization?
You haven't started acid-base neutralization.
That's depressing though.
It is kind of depressing
Where it
because it
makes the
gets
water and
wickedly, wickedly complex in about 3 weeks. Bring your A game. Is it too late to drop? Okay. Can I take this pass-fail? All right, so just now that we have those important questions out of the way, let's move on. All right, here is another one of those so sorry for you moments. Lewis acids and bases will no longer be taught in the scope of AP Chemistry next year. Well, this is not next year, this is this year. So you still have to know. But here's the good thing about it. These are supremely easy because if you look at the definition of a Bronsted-Lowry acid, it donates a hydrogen ion. The base accepts a hydrogen ion. Look at the Lewis acids and bases are exactly the opposite. An acid accepts an electron pair. A base donates an electron pair. It's totally easy. Okay. And really, all you have to know are the definitions, and you have to be able to identify one at 100 yards. Okay, here's some more vocabulary. Something that is monoprotic is an acid that is capable of donating just one proton. If you look at this, this is acetic acid. It's made of the hydrogen ion and the acetate ion. You cannot break up a polyatomic ion to donate the hydrogen ion. The donatable proton is right here. A diprotic acid is an acid containing 2 hydrogen ions. This is oxalic acid. It will lose protons. It will donate protons one at a time. That is a really big deal. Can you help me out with that?
Yeah.
Thank you. All right. Moving on.
But wouldn't those just be 2 elementary steps that when you combine them together would be 2A?
They have 2 different equilibrium constants, and there's some Le Chatelier's nonsense that goes on that makes it, it's kind of cool actually, we're just not there yet. Okay, a polyprotic acid is an acid that's capable of donating multiple hydrogen ions. A phosphoric acid is capable of donating 3. An oxyacid is an acid that has an oxygen attached to the H. You know what? That's an acid from a polyatomic ion. An organic acid is one that has carbon in it somewhere. We'll be using organic acids next week when we do a titration that is really kind of fun. You will enjoy it. Okay. A carboxyl group is attached to it. Polyprotic bases are able to accept more than one. So an anion with a 2 or 3 negative charge is polyprotic. PO4 minus 3 can accept how many protons? 3. HPO4 minus 2? 2. Something that is amphoteric or amphoprotic, it can behave as either an acid or a base. All right. Water is the big amphoteric acid or a base that we need to talk about. All right, I think that I skipped what I wanted to talk about right here. Okay, let's go back to this. All right, what is this? In this Bronsted-Lowry scheme, this is the, this is the, this is the, and this is the. All right. When we look at this going in the forward direction, we see that the acid loses a proton and the water gains it, correct? Now, if we look at it the other way, this becomes the acid, it donates the proton, and this becomes the base, it receives. See how that works? That was your question. Okay, ladies and gentlemen, the next thing I want to talk to you about is percent dissociation or percent ionization. In common everyday terms, the percent that something breaks up, breaks apart. Strong acids and bases dissociate completely, 100%. Strong acid and base, how do I even know what that is? Turn your page over. Read this. And then down here, read this. I'll get back to you in just a moment. Wake up and read that. Check my Facebook.
No copies prove to like make you a reformer or something?
I don't know.
Not too much, but just saying.
Okay, refreshed on what a strong acid and strong base are?
Sure.
You know what? You just absolutely positively need to know this. And I don't know any other way other than for you to memorize them. Because you will get these wrong if you haven't. And really, look, there's 10 things to memorize. You can do it. Back here we are. Okay, if you're talking about an acid, to compute the percent ionization, you find the concentration in molarity of the hydrogen ion compared to the concentration of the acid. That's 100%. If you're talking about the base, it would be the concentration of the hydroxide ion over the base times 100%. Strong acids and strong bases have a percent ionization of 100. Do not be fooled on any test that you take when they ask you and you think to yourself, oh my God, I can't do this math, there's not enough. The answer is 100. Weak acids and weak bases do not dissociate fully. Do not dissociate fully. So, therefore, an equilibrium expression comes about. So if you have an acid and it is not strong, it's in equilibrium to its proton and to the anion. So if you have an equilibrium association expression, you can also have an equilibrium constant for acids. That would be the products over the reactants. These are equivalent. All of this work is happening in water. We're leaving the water out. Why? Because it's pure liquid. Okay, same thing with a weak base. You can have a Kb expression as well. The smaller the Ka or Kb, you fill in that blank. The weaker the acid and the more the acid is favored. Equilibrium lies to the left. So the smaller the Ka, the more of this at equilibrium we have and the less of this. All right. What you need to know is that dissociation happens one proton at a time. So for a monoprotic acid, this is it, you're done. For a diprotic acid, you have this, and then there is another.
What?
This would be Ka1, this would be Ka2. You could write an equilibrium expression for both of these things. And I need you to take a reasonable guess about which would be bigger, Ka1 or Ka2. Come on, think.
2.
Waiting for the other right answer.
1. Neither.
1. Why 1?
There's 2.
It's not charged.
What's
I mean,
more?
a
It's like
neutral
double,
charge.
isn't it? Almost. Or not?
It's a neutral charge, so it's easier to separate.
Has to do with the French guy.
Le Chablis.
Yes, it does have, it has to do with,
Wait, what
okay,
more
so
concentration?
here you go.
There's
This
more
is your
stuff
first
on
thing.
this side.
And then this is the second thing. You got some of this floating around, right? Pushing equilibrium to the left. So Ka2 is always much smaller than Ka1. Oh. Okay. Let's look at these 4 things.
Wait, where?
Looking. And they want us to write the simple ionization reaction, omitting water, for each of the following. I want you to look at these, and I want you to raise up the number of fingers that are equal to the number of double-headed arrows that will be necessary in completing this task. Your choices are no fingers through 4 fingers. Ready? Okay, close your eyes so you can't cheat off each other too. Okay. You are going to raise your hand with the number of fingers that correspond to the number of double-headed arrows that will be used here. Close your eyes right now. I see your eyes right now. You're actually looking at me. Close your eyes. Raise your hand with the number of fingers.
For A or all of them combined?
All of them combined.
All of them.
All of them combined.
Oh wait, I gotta do them.
You should be able to just look at them. Okay, somebody has 5 fingers up. Put them down. There's only 4 of them.
I had 6 of them, okay.
Okay. Oh my gosh.
I got
All
4.
right. Let's look at this. Weak or strong?
Strong.
Strong. It is 100% dissociation. It is a completion arrow. There is no equilibrium. Weak or strong?
We.
No. Equilibrium lies so far to the right that the opposite direction is absolutely negligible. It's not. We're going to say it's not measurable by ordinary means. So yes, if it was in a closed container. Acetic acid. It's weak or strong?
Weak.
Double-headed. Ammonium. Is this an acid or a base?
It's a conjugate base,
It could be an acid, it has a proton in it.
right?
It does have proton together. It is an acid. Plus, it says for the following acids. Okay.
Why don't you ask that question?
Trust everything they ever tell you.
And this.
Double-headed.
Double-headed.
Yeah.
All right. So what?
What is that, 3 of those though?
It will have Ka1, Ka2, Ka3.
So that'd be 3.
Wait, what?
Well, you could.
Would be
Okay.
an
All
acid.
right. All right.
Why the bottom long?
All right. So I'm going to write the dissociation, the breaking apart minus the water looks like this. Acetic acid will be an equilibrium since it's weak. Ammonium and phosphoric acid.
So on the bottom right answer is that double arrow on A as well.
Yep.
Who made this worksheet?
I bought, it came with a company who has the whole thing nicely formatted. This is the only downfall to it. They're frequently not right. Okay.
Wait, go back. Oh wait, it's on the paper. Never mind.
It is. Okay, now, this is where kids get messed up. Do not be one of those kids. Do not confuse acid strength. Strength equals the amount of ionization with concentration. Concentration, the amount of solute per liter of solution. They are not the same thing. They are not even close to being the same thing. But in general usage, outside of this room, sometimes these are synonyms. Inside this room, they are not. They are not. A strong acid is one in which the equilibrium lies far, far to the left. It has such a large value for Ka that they don't even publish it. You can think of it as going to completion. All of the acid that you start with ends up as the ions. Look, here's a little picture of it. If you have this acid when you start, after dissociation, it will be completely ionized, the same amount. If you had 1 molar hydrochloric acid when you started, you have 1 molar in the proton, and you have 1 molar in the anion. Good? Okay. Now, a strong acid produces a weak conjugate base. In here, what is the weak conjugate base? Thank you. Here it is, the conjugate base. This conjugate base cannot find a acid to donate a proton to it. It's just not very interested in doing it. So a strong acid, weak conjugate base. A weak acid is one in which the equilibrium lies far to the left, and it has a very, very small value for Ka. A weak acid produces a strong conjugate base. This conjugate base is able to pull a proton to make the acid again. If you would look at the weak acid here, this is the way it dissociates. So at equilibrium, you have way more of the acid or the reactants than you do of the products. Okay.
What would be a medium acid? Would that be like 1 on the pH? Or like 2?
No, I don't want you to talk about pH here. We're going to talk about Ka values instead. And it would be a Ka value that was close to
0
times 10 to the 1, negative 1. Negative 1. That would be a strongish. Okay, may have misspoken. All right. I want you to look at this, and you could do this mathematically, or you could trust me that it's true. Which would you like to do?
Trust you.
Okay. Here is acid concentration, and that would be the amount of solute in the solution, and the percent ionization, and this would be the breaking apart. As the amount of solute increases, what happens to the percent that breaks apart? It decreases quite a bit. It decreases quite a bit. So if you want more of your weak acid to ionize, would you use a small concentration or a large concentration? A small concentration. All right, we can skip this for right now. And let's talk about the auto-ionization of water. What? The transfer of a proton from one water molecule to another? True, here it is, right here. So, at any given time in your beaker of water, some of your molecules of water are doing Bronsted-Lowry acid-base stuff. And this is how they're doing it. One of these, let's call this the acid and this the base. The acid is donating its proton to become a conjugate base, and another molecule will be accepting that proton to become a conjugate acid. Got it? This is an equilibrium expression which gives rise to another equilibrium constant, Kw. That's the equilibrium expression that expresses this reaction, otherwise known as the auto-ionization of water. This is just a few molecules of water in a beaker. Not all of them do that. But they're enough that it produces sometimes an inequality of hydrogen ion to hydroxide ions. The equation that we would use to write the equilibrium equation for this reaction would be this. Remember, these are aqueous, these are pure liquids, these aren't in the expression, these are. So Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. At 25 degrees Celsius, under normal conditions, this is a constant number. It always equals 1.0 times 10 to the negative 14. So, if this was 1 times 10 to the negative third, this must be 1 times 10 to the, remembering that it always equals 1 times 10 to the negative 14. This would have to be 1 times 10 to the negative 11. Okay, you get how these are related? All right. And actually, this is what this is right here. All right. So if you check out the molarity of the hydroxide ion concentrations, and you find it's equal to the hydrogen ion concentration, it's a neutral solution. Go ahead and drink it. If you find that the hydroxide ion concentration is greater than the hydrogen ion concentration, the solution is basic. Don't drink it. And if the hydroxide ion concentration is less than the hydrogen ion concentration, it is acidic.
Go ahead.
I don't know.
Go ahead.
How do you know?
Depends.
You can
It
pick one to
depends.
choose, that's-